This video is going to cover variable benefits and conventional with-profits policies from the topic of contingencies in actuarial mathematics. So I'm going to have to break this section down into, I think, 3 parts. The first part I'm going to cover assurances that have variable benefits. So the benefits may increase discretely, continuously, or at a certain rate, etc., etc. And then I will cover increasing life annuities in the second video, and then the third video I'll probably be dealing with the difference between with profit and without profit policies and some theory there regarding interim bonuses, bonus loading, how annual bonuses are added, simple compound, super compound, etc., etc. Okay, so let's first start with variable benefits. Okay, so assurances that increase throughout the term of a policy. So these death benefits may increase at a constant compound rate. They might increase by a constant monetary amount. And so I'm going to be dealing with first all of these cases, but first of all, payments varying by a constant monetary amount. So here, the expected present value of this assurance contract will be the sum to infinity from k equals 0 of 1 plus b to the k, where b is this growth rate of our benefit, times by v to the k plus 1, so we discount this, and then times by this deferred probability. So the probability that this person aged X dies in any given year, but now I must pick that actual year, so I have to defer this death probability by k years. Okay, so let's understand what's going on here. So if I have a life that's now aged X, my first index is k equals 0. So that means that when k equals 0, I'm not growing this thing at all. It's 1 plus b to the 0. That's just 1. Then I'm discounting by v to the 0 plus 1. So I'm discounting by 1 year. So I'm assuming that this benefit that covers him in the first year of life, it's payable at the end of year of death, over there at time equals to 1. So I discount it by 1 period. And then this must be when 0 deferred qx. So this is just the same as 0 qx is just equal to qx. So the probability that the person dies within that year. So if the person dies within that year, I'll be discounting a payment from x plus 1 to x, or from time 1 to time 0 in terms of time, and then that payment would not have been grown. Okay, so I'm assuming that is a unit size, of size 1. Okay, now if k equals to 1, then this person would be aged x plus 2. So if k equals to 1, then 1 plus b to the k. So here they'll just receive 1. But here, if they die between ages x plus 1 and x plus 2, then this index is 1. So I have a payment now of size 1 plus b. And that must be discounted by v to the 1 plus 1, 2 periods, 1, 2. And then this is a probability 1 qx, which just means the probability that the life survives 1 year, and then the life aged x plus 1 must die in the next year, so in this year. Okay, and that goes on until infinity. Okay, so in actuarial notation, the way that we're going to denote this increasing assurance is going to be as such. We'll have 1 over 1 plus b axj. Okay, so I need to find j here. J is this new interest rate that I'm getting out. So j is going to be the interest rate that accounts for the growth of these payments. So what's essentially happening with these payments, so the payment at age x plus 3 would be of size 1 plus b to the 3. So if the person dies between age x plus 2 and x plus 3, they'll receive that size payment. So the payments increase in a fashion like that, a compounding fashion. And whenever the person dies, they'll get that size of the payment. Okay, so J must represent, instead of now trying to think of a new way to do these formulae that's obscure, what we're essentially doing is we're building in this growth rate into the interest rate, and we're coming up with a new theoretical interest rate that's not actually the interest rate, but we're going to be using this theoretical interest rate as J, so that we can still work with assurances that we know of just one effective size, if you understand what I'm saying. So what we're then doing is V will be 1 plus I to the negative 1. B is our growth rate. And so when I group those two together, I would get 1 plus B over 1 plus I to the K. And then that'll be times by, or let's just put up here, plus 1. And then outside here, I must multiply by this 1 over 1 plus b. Okay, so essentially I'm just dealing with these two terms in this summation. So what I've done here is I've converted this v to 1 over 1 plus I. I've taken this 1 plus b to the k in here. I've also multiplied it by another 1 plus b to the k to get this extra exponent that I didn't have over here. And if I must multiply it by 1 plus b, I must also divide by 1 plus b to keep it the same size. Okay, now this becomes 1 plus b over 1 plus I becomes our new v, our v star. This is our 1 over 1 plus I star, or rather our 1 over 1 plus j. Okay, now we have to solve for j here. So j then equals 1 plus I over 1 plus b minus 1. Okay, so j is then our new interest rate, even though it's not actually an interest rate. It's our new compounding rate. Okay, so I've got to take that 1 over b out, because I'm dealing with this ax to the j, which just deals with this part of it. So I'm basically replacing like v to the k plus 1 with this, and then this 1 over 1 plus b must come out. Okay, and then the v would then be at an interest rate of j. Okay, so let's move on to the next one. So this is going to be when payments are varying by a constant monetary amount. So in the previous example, I had payments increasing as such, but now I'm going to have payments that increase discretely. So at age x plus 1, this person could receive a unit size payment. At age x plus 2, they would receive then a payment of size 2. So if that's of size 1, then that would be of size 2. Then at age x plus 3, they would receive a payment of size 3. And that would go on and on and on. But now, this is of course still, if they died within the year, then they receive the payment at the end of that year, and whatever size that happens to be on this timeline. Okay, so how do we write this? So for a whole life assurance, the expected present value will be equal to the sum to infinity from k equals 0 of k plus 1 into v to the k plus 1 and then k qx. Okay, so the actuarial notation for this is IA x, like that. And you should recognize similar notation from financial maths for increasing annuities, except now these are increasing life assurances. Okay, so contingent on life, hence why I have probabilities in here. Okay, so how does this formula make sense? Well, when k equals 0, our first index, that means this will be 0 plus 1, which is just 1. So my payment is of size 1. Then I must discount it by 0 to the 1 time period, 0 plus 1 time period. So v to the 1 is my discounting factor. I just discount it by 1 period. Then I have 0 qx. So this is essentially just the probability that this person age x dies within the next year, deferred by no years. So in this next year exactly, so aged x. So the probability that this person dies aged x. So dies within this year. So if they die within this year, they'll receive a payment of size 1, and then I'll discount that back to age x, or time 0. Okay, now if the person dies between age x plus 1 and x plus 2, I'm dealing with k equals to 1 here as the index. Now k equals to 1, I have 1 plus 1, that's 2, so my payment is of size 2. If my payments of size 2 happens at time point 2, or at age x plus 2, then I discount this by v to the 1 plus 1, 2, so 2 time periods, and then this is a deferred death probability by 1 year. So the probability that the person survives for 1 year and then dies in the year succeeding that. So survives to age x plus 1 and then dies aged x plus 1. Okay, and then you can continue counting up with these indices and you'll see how we'll get the next payment and so on until infinity. Okay, so that's a whole life assurance where the payments increase by a constant monetary amount. Okay, now let's talk about term assurances. So here, the expected present value, let's use a new color. The expected present value will equal to, in actuarial notation, IA x n. Okay, so very similar notation. You can start to see how these notation actually mean things and make sense. You can tell a lot about how this assurance is actually behaving just by the notation. Okay, in fact, you can tell everything. You just don't know the interest rate, you don't know mortality assumptions, but all that's specific to the scenario. You know how the assurance behaves. This equals to IAX minus v to the n npx into IA x plus n plus n times by a x plus n. So this needs some explanation. Now this is not actually something that you need to memorize. It's quite intuitive, so I'm going to explain it to you. Okay, so what I'm essentially dealing with here is a term assurance contract, but the payments increase throughout the term. So it looks very similar to this, except it stops at some age x plus n. So they aren't covered beyond that age. They have to die before then, okay, within the next n years. Now, what I'm essentially doing is I'm taking a whole life assurance, so one of these things that covers them for the entire of their life, and then I'm subtracting another whole life assurance, but except from time point n, from age x plus n. So this is the whole life assurance at age x plus n. But then you must note that this alone starts with a size payment of 1. But this, by the time it gets to x plus n, has already increased in size. So if I'm subtracting all these payments beyond age x plus n, I'm going to have a mismatch. So let me explain exactly what I'm talking about here. This is at time 0. This is at time 1. There's a payment. At time 2, there's a larger payment. 3, larger payment, etc. And this takes me all the way until n, where there is a large payment. And then here there's n plus 1 with an even larger payment. Okay. Don't mind my bars, they don't actually matter. Okay, but just generally what these should represent is a unit increase from bar to bar, from payment to payment. Okay, so here, this represents all of these payments going on until infinity. This assurance over here, this increasing life assurance. Now this increasing life assurance represents all of them beyond time point n. So this one represents the assurance, the term assurance between 0 and n. So all of these ones. So in order to get all of these ones, I have to take all of these and subtract all of those. Okay, that's my goal here. So if I am to do that, what I'm basically looking for is to remove these payments, all these ones that happen over here. If I am to remove this payment, I have to remove a payment of size n plus 1. Okay, how do I get a payment of size n plus 1? Well, this has a payment of size 1 at age x plus n plus 1. So if he dies aged x plus n, between n and n plus 1, he will receive a payment of size 1 given this. But I need to be subtracting a payment of size n plus 1. And so I must add a whole life assurance of size n to that to make this n plus 1. So here's the n and here's the plus 1. And this plus 1 will come from this. And then the next one at age n plus 2, the n will come from here, this this whole life assurance, constant whole life assurance, and then this one will account for 2 sizes. Okay, etc., etc. So I subtract those together in order to cancel out all these other payments, just so that I'm left with this term assurance. Okay, and then of course I must multiply what I'm subtracting by v to the n npx, because all of these bring the present value to time n, but I need the present value to be at time 0 in terms of both probability and time, and so I have to subtract. So I have to discount those by a further n years in terms of probability and time value of money. Okay, so I hope that's clear. Now moving on to endowment assurances. So this should be relatively simple. So here I have the notation IAXN. So note I don't have a line here on top of the x like I did for a term assurance. And this equals to this increasing term assurance plus a pure endowment, hence the line on top of the term here. So a pure endowment of size n. Okay, so why is there a pure endowment of size n? Well, this is an increasing endowment assurance. So if this person survives to the end of the n years, then they have to receive this amount that's increased for n years. So they have to receive this payment of size n if they make it to the end of the contract. And so that comes from this pure endowment assurance. Now, why do I not just say here something like this? Well, it doesn't make sense because this is our pure endowment will only pay at one point in time. So it's not increasing throughout the term. Okay, so it doesn't make sense to write it as an increasing assurance. This pure endowment part of the endowment only makes a payment at the end of the term, so we don't need to write it as an increasing thing. This is not necessarily wrong, but it is theoretically wrong. This is not defined. This is not a defined symbol. So we mustn't use this. We just take a pure endowment assurance and we multiply it by n in order to rescale it. Okay, now let's talk about a decreasing term assurance. So this requires a little bit of understanding, so I want to walk you through that as well. So here, the expected present value of a decreasing term assurance will be equal to n plus 1 into AXN minus IAXN. Okay, so what I've essentially done here is I've taken a term assurance of size n plus 1 and I've subtracted an increasing assurance. So what I'm then doing is here at time 0, this is of height n plus 1. At time 1, n plus 1, etc. all of these of the same height until the end of the term from this. Now, what I actually want is something that's decreasing. So I want something that looks like this. Okay, now, my apologies, this should not be here. Why should it not be here? Because assurances never pay in advance. Why can't they pay in advance? Because you can't pay someone in advance for their death. You don't know that they're going to die. Okay, that's extremely corrupt. That doesn't make sense. It's like that would be it doesn't make sense at all. It would be a disaster. Okay, so here, what I'm actually looking for with this decreasing term assurance is something like this. Etc. And then it can decrease all the way until the end of the contract, and decreasing by a unit each time. So now, in order to get this decreasing shape, I can take a constant assurance contract and subtract an increasing assurance contract. Okay, so the yellow lines minus the green lines will equal to my purple lines. So that's the understanding behind this. And I'm going to start with n+1 for my term assurance, not increasing, just this constant term assurance. I'm going to start with size n+1 because I'm going to be subtracting a payment of size 1 with this increasing assurance at time 1. Okay, which will bring this purple line to be of size n. Here it'll be of size n-1. Here it'll be of size n-2, etc. All the way to, at the very end here, there actually shouldn't be a payment at time n, and there'll be a payment of size 1 at time n-1, and that'll be of size 0. Okay. Now, last thing I'm going to deal with for this video is increasing assurances payable immediately on death. Okay, I've been thinking about this, and okay, this should actually be of size 1, and that should be of size 2. Okay, why should it be the case? Well, because this is going to be a decreasing term assurance, and these decreasing term assurance pays the death benefits are payable at the end of year of death. So what that means is that I have n possible places to pay this person. And if this is 0 over here at the end of the contract, it means I'm only paying them in an n-1 possible points in time. It doesn't make sense for a term of n where there could be a payment in any given year. Okay, so it doesn't make sense. So this has to be 1 at time n. Okay. Now, increasing assurances payable immediately on death. Now, the actuarial notation for this is IAX, and this has the approximation equal to 1 plus I to the half times by IAX. So this is the claims acceleration approach that I've explained in previous videos. So if you'd like to understand that, then go and watch the life assurances contract videos in the contingencies playlist on this channel. Okay, so that's it for assurances that are increasing. In the next video, I'm going to be covering annuities that increase.